A serious flaw was present in the first carbon pile concept and its accompanying video. The underlying mistaken premise was that the heat generation in spent nuclear fuel rods was due to nuclear fission. In fact, the heat is actually being produced by radioactive transmutation decay, not by atom splitting. Because of this, once a spent nuclear fuel rod was melted into a carbon fiber pile, it would not cool and solidify, but remain molten for 2 to 20 years, depending on the composition of the fuel rod, but usually between 10 and 20 years. However, as it turns out, this is actually a very useful and highly beneficial thing. The facts regarding the real source of the heat production are actually more reason to convert the fuel rods into carbon fiber piles, even though the original reasoning was mistaken. Manufacturing these piles will serve 4 very useful functions. 1. It removes the volatile radioactive isotopes out of the fuel rods in a controlled manner without any release of radioactivity. 2. It eliminates the danger of spent nuclear fuel pools. 3. It immensely improves the safety of the reactor, by providing a more reliable backup for the circulating pumps and reactor control systems. 4. It makes the reactor operator a very large sum of money. For example, if the Fukushima plant was still operating, TEPCO would be making an additional $2 million a year at Fukushima. First, let me explain the ramifications of melting the fuel rods. Let the fuel rods melt, under their own decay heat, in a proper custom-sized crucible in a vacuum chamber. This will release all of the dangerous fission products from the fuel rods such as radioactive iodine, cesium, strontium and so forth into the vacuum chamber. Release the vacuum slightly with the addition of nitrogen, then evacuate the nitrogen and volatiles into a low-pressure storage tank, and repeat until all of the volatiles have been collected into the tank. Or, operate at atmospheric pressure rather than vacuum, and use a powerful ventilation system and filters to catch the volatiles. All of the dangerous volatiles will resolidify, in the tank, or in the filters. This is why spent fuel pools are safe as long as they are cooled with circulating water. The volatiles are solid at normal terrestrial temperatures, but are vaporized into gaseous form when heated. At this stage of processing, the molten spent fuel rods are much safer. While still emitting large quantities of ionizing radiation, which they will continue to do for a very large number of centuries, they cannot produce or release any significant or dangerous quantity of dangerous fission product isotopes again. Only operation at critical mass inside a nuclear reactor core can cause any significant degree of fission. Critical mass is a very nuanced and involved subject, and it takes some effort and research to fully understand it. My lack of research initially led me to the same belief, that significant fission would still be occurring in spent fuel rods, when in fact, this is not the case unless you place a very large number of fuel rods very close to each other. Once the fuel rods have been processed to this stage, and afterwards when they are absorbed into the carbon fiber piles, they will only produce measurable and dangerous levels of ionizing radiation, and radon gas. Pour the molten fuel rods into the carbon fiber piles. The piles will not cool and solidify, because of the decay heat being produced. The carbon fiber mass will remain solid, plated with molten corium. At this stage of processing, the piles could remain in the molten state, and the concrete boxes could be relatively safely stored in a sealed warehouse, as long as there was a basement to collect the dangerous radon gas. After 10 to 20 years, the piles would cool and resolidify. Never mind the potential safety issues, because storage in a warehouse is not going to be the destination of the molten piles. Flood the vacuumed chamber with circulating steam, using the reactor's steam supply, until the temperature of the piles is the same as the steam temperature and the plated corium has solidified. Then, transfer the piles into a fairly large-sized cooled water storage pool with a circulating system, similar to the spent fuel cooling pools. Stop the circulating water to this pool, and what will happen? The water will boil, then all the water will boil off, and the piles will melt again because of decay heat. There would be no release of radioisotopes, only radon, which sinks to the bottom of the pool because it is heavier than air or water. To recover, you would have to cover the pool and inject steam to cool the piles to the temperature of the steam, and then restore the water and the circulation. The issue of dangerous spent fuel pools has been resolved. What used to be the fuel rods can still meld, but cannot release any dangerous fission product isotopes. But let's say that you installed the piles into a much smaller pool, vastly increasing the ratio of pile to water, in favor of the piles. The water would boil off, much more rapidly. In fact, this is very highly desirable, because the piles will not be stored in water pools with cooling systems, but inside of a steam boiler to generate steam. Remember, the rarefied volume of fissile uranium in the piles can no longer support criticality. The heat will be produced entirely by decay, not by fission. The boron trioxide can be recovered and reused, and neither the corium or the carbon fiber will corrode a steam boiler. Apparently, a single molten fuel rod assembly gives off much more heat than a 5,000-watt generator engine does. Let's examine the spent fuel pools at Fukushima. At the time of the accident, the reactor spent fuel pools and central storage facility contained the following numbers of fuel assemblies. Unit 1, 292 assemblies, Unit 2, 587 assemblies, Unit 3, 514 assemblies, Unit 4, 1031 assemblies, Unit 5, 946 assemblies, Unit 6, 876 assemblies, and central storage, 6,375 assemblies. The 6,375 assemblies in central storage will be ignored here since no data is readily available regarding their ages. Assemblies older than 20 years do not produce enough heat to meld, and would be unsuitable for steam generation. Ignoring those, we had a total of 4,546, less than 18 months old, spent fuel assemblies in the cooling pools in the reactor buildings. Why waste electricity from the main reactor turbine, that could be being sold into the power grid, to power circulating pumps to cool the spent fuel pools, when you can use the spent fuel pools to safely produce electricity, instead? Do the math. If each assembly produces as much heat as a 5,000-watt generator engine, then 5,000 watts times 4,546 assemblies times 0.033 steam generation efficiency equals 7,500,900 watts, or 7.5 megawatts. A continuous 7.5 megawatts annually is 65,707,884 kilowatt-hours, worth $1,971,236 at 3 cents a kilowatt-hour. So, instead of wasting electricity from the main reactor turbine to power the circulating pumps to cool the spent fuel pools, the grave dangers associated with the spent fuel pools can be outright eliminated, and the reprocessed spent fuel rods can produce $2 million of electricity annually. At this stage of processing, the dangers associated with the spent fuel rods and pools have been eliminated, and the means of turning a dangerous liability into safe assets and profits is available. But wait, it gets even better. 7.5 megawatts is a lot of power. Why run the circulating pumps for the reactor vessel itself from the main reactor turbine, and rely on backup systems and a power grid that were proven to be disastrously unreliable at Fukushima? Old technology can save new technology. Search the internet for steam engine restoration, and you will see that blacksmiths still exist who now use modern technology, who have kept the art of the steam engine alive. The steam turbine cannot beat out the steam engine for non-interruptible power, because the steam turbine will automatically trip and go offline in an earthquake. If you mount it on shockproof rubber footings, the steam engine will ignore an average earthquake. These spent corium pile boilers, or perhaps more accurately, depleted corium pile boilers, allow for a system where you might have 7 megawatt turbines in operation continuously, with one operating the reactor cooling pumps and reactor control room, and 6 others that can be instantly switched in to replace the active unit, backed up by 3 1-megawatt steam engines, backed up by 4 separate battery bank systems and diesel generators. The battery banks only need to operate long enough for one of the 3 idling steam engines or a diesel generator to come up to full power generation capacity, 20 seconds at most. There should be multiple reactor circulating pumps in case one fails, and each should be powered by a separate turbine, steam engine, battery bank, and completely isolated and protected power grid network. As evidenced at Fukushima, the current reactor cooling strategies are not robust enough to provide a high degree of defense against a core meltdown caused by a coolant loss, and these methods can easily raise the minimum reactor safety standard to an acceptable and effective level. Given provable internet censorship, this internet posting therefore does not qualify as a public disclosure, and all patent rights remain with my employer in Japan, Mitsubishi Corporation, as already witnessed by the foremost members of the WTO. In closing, I will make a better replacement video, but I wanted to rapidly get this out to those capable of bypassing the censorship, and so I post this now, while I work on a more illustrative video. Also, the basic design for a carbon fiber and boron trioxide core catcher is coming into clearer view, which involves the relatively inexpensive action of adding 10 feet of height to the reactor pressure vessel to make room for the carbon fiber pile at the bottom. I currently have no decent microphone, but I may have been a limey in a past life, and so the computer synthesized voice works well here.